Hello and welcome to the Chapter 4 podcast in Section 4.6. Today we're going to be talking about solution stoichiometry and titrations. Basically, the strategy for doing solution stoichiometry is the same as the stoichiometry we did in the last chapter. We're still using mole ratios, but now we have something in the denominator, the volume of solutions. So in order to get moles of our what we have to start with, we're going to have to multiply it times the volume that we're adding. So we're not just mixing grams and moles together. We're actually, literally mixing liquids together, which means that the moles are dissolved inside of the liquid. So we have what we'll often start with is if we have, we'll have our strategy that we'll use here, and a lot of this is going to depend upon the way the problem is written, and there are many different kinds of stoichiometry problems that we're going to be doing, and it's something that we're going to practice quite a bit, not only in this unit but also other ones. So this will be like one of the recurring themes that we'll be using throughout the course. But here's an example of one. If we want to, here's a situation where we have one solution and then we have one dry reactant, and this happens sometimes. So this is one type that we would do. Let's say we had 20 milliliters of a 0.15 molar acid solution of sulfuric acid, and I want to know how many grams of sodium hydroxide are needed to neutralize it. Well, remember, to do stoichiometry, you always have to have a balanced equation, and a lot of times at this level, they'll actually expect you to write out the equation yourself. So this is just an acid-base neutralization reaction, which is double replacement, and so we put together our products and then we balance the equation. We know that we want, in order to do this, if I have 20 milliliters of a 0.15 molar solution, I need to know how many moles of H2SO4 are in that volume. So we use our molarity triangle to calculate moles. So I multiply the molarity times the volume. Then what we know, once we have moles of H2SO4, we can use our mole ratio from our balanced equation to go from moles of H2SO4 to moles of NaOH. So once I know how many moles of sulfuric acid I have, because it's a 2-to-1 ratio, I know I have I would need twice the amount of moles of sodium hydroxide. But I don't want moles of sodium hydroxide, I want grams of sodium hydroxide, so I'm going to have to convert my moles of NaOH to grams. And this is illustrated here in this first step. So we multiply the molarity times the volume. That gives us moles of H2SO4. Here's our 2-to-1 mole ratio from our balanced equation. And then the 40 grams over 1 mole is our conversion of grams into grams of NaOH. Okay. Let's say I give you another example. So let's say we have 0.100 moles of Pb of lead 2 nitrate, and I want to know how many liters of a 0.5 molar solution of hydrochloric acid are necessary to react with it. Again, we'd have to write out our reaction. So this is a double replacement reaction again, and we're going to use our moles to find out how many moles of HCl are necessary. We can already see that it's going to be double of whatever amount of lead nitrate we have, lead 2 nitrate we have. And then we can use our triangle to find liters. So we would take that answer and we would multiply it times the inverse of our molarity. So and this is illustrated here in the calculation on the bottom. We have our 0.1 moles of lead 2 nitrate. Our 2-to-1 mole ratio comes from our balanced equation. And then what you see here, this last thing, is the inverse of our molarity. And remember, capital M, we can always break it down into moles over liters. And since this is the inverse, that's why it's 1 liter, the liters over moles in this case. And all of the units cancel out, as they should. Titration is what they're referring to as a way to do an analysis. It's used quite a bit in industry and in research, and titrations are something that you will be doing quite a bit of in college, and we'll probably do a few in here as well. We may start doing these as computer simulations first so that you kind of understand the concept. But basically, we have a sample solution, and then we basically add another solution where we know the concentration of, and we call this our standard. Okay, there are many different kinds of titration types, but the ones that we'll focus on are acid-base, precipitation, and redox. Okay, these are just some household terms related to titrations that you need to know. The equivalence point is basically when you have stoichiometrically equivalent quantities. So what that basically means is that you got to the point where the mole ratio has been achieved. Okay, so if it's a 2-to-1 mole ratio, you're at 2-to-1, or if it's 1-to-1, you're at 1-to-1 at that point of adding the standard. Indicators are often associated with titrations. These are dyes that change color during certain kinds of titrations, most usually acid-base reactions. And the idea is that we choose indicators that are close to where where the color change occurs is hopefully close to the equivalence point. The endpoint relates to the indicator. This is where the indicator changes color, and we choose. There are many different indicators, hundreds of them, but we always try and choose an indicator where the endpoint and the equivalence point are very close together. Okay, and that's something that'll make a little bit more sense when we talk more about acid-base titrations in more detail later in the course, but just to kind of lay the foundation now. So this is what it looks like. Here's our sample that's being added. So this is what we're titrating. The standard actually goes in here, okay? Standard procedure, so this long glass tube is called a burette, okay? And the standard solution always goes in the burette. We never wash this solution. We never wash the burette is a very sensitive thing because it measures very specific volumes. We always rinse the burette with the standard solution before we start because we don't want water diluting out our sample and messing up our results. That's how sensitive some titrations can be. And basically, you have an initial volume, and basically you're going to continue to add until you get to the end point, or a neutralization point, which is where the color change should be. And the difference between your initial and final reading is how much you added, and then you can use that volume to calculate the molarity of this acid solution. But you have to be very careful when you get near to the end point, because some people, if you add too much solution at the end of the standard, you can blow right by and not realize it. And this is one of the reasons why we don't do a lot of these in class, because you basically get maybe 1 or 2 shots at this, and if you mess it up, it's very difficult to start over. The first calculation for titration is basically where we're determining an amount of solute. In this particular example, we're doing an ionic equation, and here I have we've titrated iron with 47.2 milliliters of a 0.02240 molar permanganate solution. So here we can see that we can see the mole ratio. This equation was given in the problem. So if I want to know how many grams are in the sample, I can figure out how many moles of MnO4 we added, and we can take advantage of our 5-to-1 ratio. And then once I have the moles of iron, I can multiply that times the molarity of the molar mass of the iron to get the mass. So the purpose of this first step is I multiply the volume times the molarity to get the moles of iron, the 5 moles of permanganate. And then once I have the MnO4, I know that I have 5 times the amount of iron. But I don't want moles of iron, I want grams of iron, so I multiply by the molar mass. So this is how much iron should be in the sample based upon our titration. And you can see it's a very specific number with a lot of sig figs. And with the titrations, we tend to want to be very specific. But that's not the only way to do it. We can also do solution concentrations. So let's say I have 48 milliliters of an NaOH solution, and I neutralized a sulfuric acid of 35 milliliters and 0.144 molar. Okay, so here's one where we have to write out the reaction. And we see that there's a 2-to-1 ratio between NaOH and H2SO4. We can use our H2SO4. If we multiply the volume times the molarity, that'll give us moles of H2SO4, right? And once we have moles of H2SO4, we know that for every mole of this, I should have 2 times the amount of NaOH. And then once I have moles of NaOH, I can multiply by the molar mass. All right, oh, sorry. Once I have the moles of NaOH, we want the molarity of the solution. I forgot. So we're going to take our moles of NaOH and we're going to divide it by our volume in liters. So we use our molarity triangle to get our H2SO4. So we multiply our volume of acid times the molarity of the acid. The 2-to-1 mole ratio comes from our balanced equation. So now we know we have how many moles of NaOH we have. But we want the molarity of the solution. We don't want the grams of NaOH in this case, as I messed up earlier. So we would divide, I don't know why I don't have a line there. So we would divide this, the moles, by the volume in liters. So notice how I divided by 1,000 to convert my milliliters to liters. And here's our molarity. We're going to be doing a lot of these in class, so save this for reference and we'll continue.